Okay, so this video is just going to be some more examples, some other ways of using and seeing implicit differentiation to hopefully give you a better understanding and better grasp of these problems. We're going to start with example 2. Find dy dx for the relation given below. This is the relation x cubed times the sine of y plus y equals 4x plus 3. This is a relation that really makes sense to use implicit differentiation because not only is this not a function, y is not a function of x, but solving for y is pretty darn near impossible. I think it's probably literally impossible. But I only claim it's outside of my abilities. I'd have to go a little deeper to show that it was literally impossible. But basically that sign and that other term are giving us the problem. We could graph this and see what wacky thing this looks like if we wanted to. X cubed times the sine of y plus y equals 4x plus 3. Yeah. Yeah. We're not solving for y on this one. But we're going to talk about the derivative. You might look at that and say, Jason, that is so wild. I'm never going to be able to find the derivative of this crazy, not function, but relation. Well, we're gonna do it together. I had actually not graphed this before. It is wild. I like it. Okay, cool. Let's get going. So what were the steps? Even if you don't remember the steps, there's some logical ways for you to think about it. We want to get the derivative of y with respect to x. So we need to take a derivative with respect to x. All right. And that was our first step. Take the derivative with respect to x. d dx both sides. If two functions are equal, if two things, these aren't functions anymore. If two things are equal, then their slopes have to also be equal. That is why we can take the derivative with of both sides. There's some other more technical reasons why as well, but that's what we're going to start by doing. Taking the derivative of that left-hand side and it's not going to fit. And take the derivative of the right-hand side. I'm just going to write it on, I'll write it on a new line. Okay, so take the derivative with respect to x of the left. And that'll be a little fun. And then take the derivative with respect to x of the right-hand side. That one will be a little easier. So first off, there's a lot going on. For many, many reasons, and don't write this down, you can't just say this. Okay, there's two problems with this. First off, it's one function times another function. We're going to have to use the product rule. And two, we're not taking the derivative with respect to y, so it's not just cosine. We're going to have to use implicit differentiation. It's the chain rule. Y is dependent on x. So when you take that derivative of sine of y, you're going to have to also include a dy dx. Your chain rule always has you multiply by the derivative of the inside function. This is going to be a little messy. Let's go off to the side and say that's f, that's g. We need the product rule. So let's come off to the side real quick and say, okay. So product rule says f prime g plus fg prime. And we know that f prime is 3. You know what? I always skip this step and I always regret it. F of x is x cubed. F prime of x is 3x squared. Now we can do the same thing with the blues. G of x is it's not a function of x. Oh man. Let's not worry about that too much for now and just write that g is sine of y, and the derivative with respect to x of g, that's going to be the cosine of y times dy dx. All right, because we're taking the derivative of g, which is a function of y. Yeah, we should write it like this, g of y, if we want to be really precise. The derivative of g with respect to x is going to be this. Now the product rule says this. So that's what we bring over here. This is going to be f prime g. F prime is 3x squared times g, which is the sine of y, plus fg prime is x cubed times cosine of y times dy dx, or y prime. So that's just the derivative of this guy. We also need the derivative of this. The derivative of y with respect to x is just dy dx. So that's the derivative of the left-hand side. Remember your product rule, your quotient rule, your chain rule, implicit differentiation. You might have to worry about derivatives of inverse functions. You might have to worry about derivatives of trig functions. There's a lot of derivatives that we have right now. And in 3.9, we're going to talk about derivatives of exponential and logarithmic functions as well. So there's a lot of things to keep in mind when you're taking these derivatives. The best thing you've got going for you is your ability to check your answers, which we'll do especially in the next video when we talk about tangent lines. But anyway, the derivative of the right-hand side is just 4. The right-hand side is a line. 4x plus 3 has slope 4, or you can use the power rule. So that was our first step. We took d dx of both sides. And now we need to follow the second step, which said get everything with dy dx on one side, all on one side, and all the other terms to the other side. Okay, so this term doesn't have a dy dx, lob it over to the right. Okay, so we're going to have to subtract it from both sides. And then I think that should be it, right? Everything else, that's in the right place, that's in the right place, and that's in the right place. So good. Step 2 should be complete now. X cubed cosine of y dy dx plus dy dx equals 4 minus 3x squared sine of y. Step 2, complete. This is a thumbs up. This is not a 1. This is a thumbs up. And now it's step 3. Step 3 said to factor and solve. So we're going to factor out dy dx, and should be easy to solve for it because we can just divide out by what's left over. So factor out a dy dx. When we factor it out of this term, what's left over? X cubed cosine of y. When we factor out dy dx from this one, what's left over? And be very careful, the answer is not 0. Right? If I factor out a 4 from 4, it's 4 times 1, right? It's not 4 times 0. 4 times 0 would be 0. There's a 1 left over in the parentheses. And the right-hand side's just chilling. It's just relaxing. And now, part 3, step 3 was two parts. Factor and solve. Well, we want dy dx by itself, so just divide this over. We're going to get that dy dx equals 4 minus 3x squared times the sine of y divided by x cubed cosine of y plus 1. And sometimes you might be able to simplify. You might be able to factor and cancel. But here, neither the top nor the bottom factors, and you can only cancel if everything is completely factored. You can only cancel common factors. So that is the derivative of this beauty with respect to x. All right, and a lot of times we would plot the function and its derivative to check our answer. But the problem is you can't graph this derivative, right? Is the function of x and y. I mean, you could, but it would be a three-dimensional graph, and we're not worrying about that just yet. Not in this class anyway. Let's do one more problem. Oh, it's not part B. Just kidding. I lied. Example 3. This one's really good. Find the second derivative of y with respect to x. For our circle, x squared plus y squared equals 25. Whoa. So we already found dy dx from the first video, right? We already know, oh my word. We know dy dx from the first video was negative y over x, I believe. Or was it x over y? I think it was negative x over y from that first video. It was indeed negative x over y. Well, that's the first step in finding the second derivative, just like before. The first step to finding the second derivative is to find the first derivative. That hasn't changed. Well, how do we find the second derivative? It's just like before. The way to take the second derivative is to find the derivative of the first derivative. How do we take the derivative of this? How do we find the derivative of this? Well, we're going to have to ddx both sides again. That's how you take the derivative. So we want the second derivative. Let's ddx the left-hand side. And let's ddx the right-hand side. So this is going to be a little fun. So what is the left-hand side? We're just taking the derivative of the first derivative. The left-hand side is just the second derivative. This is where the notation comes from, d squared y over dx squared. Because there's, again, it's not algebra. It's just the notation. It's just notation. We're not actually multiplying two d's together, but that's like an intuitive way to remember. Okay, well, now there's two d's, so we write d squared. And on the bottom, there's two dx's, so we write dx squared. Again, that's not actually what's happening. We're not multiplying dx by dx, but that's where the notation comes from. That's why we do it this way. But we're taking the derivative of the first derivative. We just have the second derivative remaining. And the right-hand side, it looks so innocent, but it's really not. It's kind of like October is right now, my cat. She's resting, and she looks peaceful, but you know there's a mess going on right there. And so that's what we have right here. We're going to have to use the quotient rule. All right. And the quotient rule, let's not go off to the side this time. Let's factor out the negative and then use the quotient rule. And the quotient rule says low d high minus high d low, square the bottom, and away we go. So low d high minus high d low, square the bottom, and away we go. And now all that's left is a little housekeeping. This second derivative, we don't need to keep writing that. That's not changing. You could also write y double prime if you wanted. These are the same. The top one is Leibniz notation. That's going to be negative y times the derivative of x with respect to x is just 1, minus x times the derivative of y with respect to x. That's dy dx. And the bottom is here. And you say, great, we're done. I'm so glad to be done with this problem, Jason. That sure was bad. We're not done. Why are we not done? So it kind of looks like a complex fraction, but it's not. This is just a function, dy dx. We can't multiply the top and the bottom by dx. Doesn't make any sense for calculus. Well, in some aspects of calculus, you could talk about the differential, but we're not going to do that. But we do need to replace. dy dx is this. So let's get everything in terms of x and y. All right. Ensure your final answer is in terms of x and y. Just like when we did the chain rule, we wanted to make sure there weren't any u's in the final answer. We had to replace, we had to substitute out that u. Well, that's exactly what we're going to do here. So we're almost done. There's just going to be a little simplifying afterwards. So this is what we have, and we know that dy dx isn't, I always forget it, negative x over y, right? Yeah. So we're going to say the second derivative, negative y minus x times negative x over y, all over y squared. And now we have to simplify the complex fraction. Okay. So multiply the top and the bottom by y. And as long as y is not equal to 0, which is already a requirement that we have, multiplying by y over y is okay. Whenever you have complex fractions, you choose to multiply by the LCD. On the top, we have to distribute. Y times the first thing is y squared. Y times the second thing, well, these y's cancel out. Negative times a negative is positive, x squared. And the denominator is y squared. This is a perfectly okay final answer. There's a lot of ways of writing your final answer here. But again, I'm going to use the original notation. The question did ask in Leibniz notation. You could write it just like this. We usually write the x's before the y's. You could write it like this. Or if you wanted to, oh, there's actually, I wasn't thinking about this when so this is a perfectly fine answer. I'll accept this, but there's actually a way nicer answer. A way nicer answer that I don't expect you to see. But look at the numerator. The numerator is x squared plus y squared. What do we know about x squared plus y squared? On this relationship, for this relation, x squared plus y squared is always equal to 25. That's our function. It's not a function. That's our relation. That's our circle. Anything on the circle, which is what we're talking about, has x squared plus y squared equals 25. So this is like substituting y at the end of a problem. We don't know y in this case. Y is implicitly defined. It's not a function. It's a relation. But we know that that numerator, x squared plus y squared equals 25. So we really could, this is a little bonus answer. I'd be very happy if you did this. You could also say the second derivative is actually just negative 5. Negative 25 over y squared. All right. So some cool stuff. Some cool stuff going on here for this problem. Let me know if you have any questions. There's one more answer, by the way. You could write this as negative x squared over y squared minus 1 as well. Lots of answers. But I'll take all of these. Let me know if you have any questions, and bye-bye.